And what's important about Maxwell's discovery is the things that are circled in yellow, that the changing magnetic field gives an electric field, and now a changing electric field gives a magnetic field. And what Maxwell was able to recognize is that this implies that a self-propagating field. A changing electric field creates a magnetic field, which itself is changing, which creates an electric field, which itself is changing, which creates a magnetic field. And so this is a self-propagating wave. And what he was able to do was to apply these four equations to what's called the wave equation. He was able to show that they satisfy the wave equation, which tells us that a changing magnetic and electric field must be a wave. He was also able to show that the speed of that wave, using these four equations and the wave equation, which we'll learn later, he was able to show that they imply a wave with a speed of... Okay, Maxwell's equations satisfy the wave equation. It means the changing electric field, which produces a changing magnetic field, etc., is an electromagnetic wave. It's a wave of changing electric and magnetic fields. And it's got a speed of v equals 1 over epsilon naught mu naught. The speed of the wave is that. If you plug in those constants, you can look up those constants, and you may or may not be surprised to find that those constants give you 3 times 10 to the 8th meters per second. Whoops. 3 times 10 to the 8th meters per second. This is light. So what Maxwell was able to show is that light is simply an electromagnetic wave. It's a self-propagating, changing electric and magnetic field. All you have to do in order to create light is to take a charge or take a magnet and change the field around it. In other words, shake it, move it. And if you move it, if you change the electric field and magnetic field with time, then that's going to create a propagating wave. If you move it fast enough, that's going to create a wave at a high enough frequency that it turns into visible light. That's really fast. So you couldn't shake it like if you grabbed a bar magnet and shook it up and down with your hand. You are creating electromagnetic waves. You absolutely are. But you're creating really low frequency electromagnetic waves. Light is up, I think, in 10 to the 15th hertz, 10 to the 15th cycles per second, right? Super high frequency. Anyway, all of those waves propagate outwards at 3 times 10 to the 8th meters per second. All of them, regardless of whether they're light, or now you can look at the whole electromagnetic spectrum, starting from low frequency radio waves to infrared to infrared to visible to ultraviolet to X-rays to gamma rays, all of that electromagnetic waves, changing electric and magnetic fields that propagate at 3 times 10 to the 8th meters per second. In a vacuum. In the vacuum, that's what the zeros here are, right? It's epsilon 0 is the permittivity in free space or in a vacuum. Mu 0 is the permeability in free space or in a vacuum. If we want to find the speed of light in something other than a vacuum, you want the speed of light in water, then we would use, and the speed of light is 1 over the square root of epsilon mu, where epsilon is the permittivity of water and mu is the permeability of water, etc. And that would be something less than 3 times 10 to the 8th meters per second. Because 3 times 10 to the 8th meters per second, we know from Einstein, is a speed limit. Nothing can go faster than that. That fact is something that not obvious from this, from Maxwell, but that's an Einstein's conclusion is nothing can go faster than the speed of light, and that's one of the keys of special and general relativity. So that was all of classical physics in a nutshell. I mean, we did it in a day or two, reminded ourselves of all of classical physics. And like I said, Einstein comes along and turns classical physics on its head. And so then the question is why? What's wrong? What's wrong? Well, let me just give you a hint as to what's wrong. What's wrong is that the speed of light doesn't appear to be dependent on frame of reference. Remember frame of reference? It appears to be dependent on the material properties, epsilon and mu, but it doesn't appear to be dependent on frame of reference. That's super interesting. And it might not be obvious, but it really does come from what we were looking at right here, is that the speed of light Like, for instance, if you're standing still on the side of the road and a car is going at 20 miles an hour relative to the road, it's going 20 miles an hour relative to you. But if you're walking at 5 miles an hour in the opposite direction of the car, and the car is traveling at 20 miles an hour towards you, you're walking at 5 miles an hour towards it, then relative to you, the car is moving 25 miles an hour. That's relative. So the car's speed is dependent on your frame of reference. Whether you're looking at the road's frame of reference or your moving frame of reference, the car's speed depends on frame of reference. What this tells you, what you're looking at right now, is that the speed of light is independent of frame of reference and it's only dependent on material properties. And there's something wrong there. So we'll come back to this and we'll talk about Einstein's solution.